Hello everyone, welcome to the lecture. So in this lecture we will cover activity questions 8.2. Okay, so let's start with the third question. So we have the given function which is the floor function of f if f is greater or equals to 0, and it's the ceiling function of x when x is less than 0. Okay, so now we have to consider the following options. We know that when x is an integer, so the floor function and ceiling function both are for both when x belongs to the set of integer, then the floor function or the ceiling function limit doesn't exist, right? At x. Okay, hence clearly these two are incorrect, because if limit doesn't exist, so the function is not continuous, and hence obviously it's not differentiable at 1 and -1. Okay, uh, so we will check at 0, and because the function is breaking at the point 0, so it is neither floor function nor ceiling function at 0, and 1.5 is a 1 point. Okay, so if we consider 1.5, then fx is a floor function at near the point 1.5. So we already know that the floor function is a smooth function near any non-integer point, right? So it's always differentiable, so this is correct. We will check at 0. Okay, so okay, limit h tending to 0, we will directly check the differentiability. Okay, so we know that the definition if h, because we are checking at 0, so this will be h plus 0, so it is again h. Okay, so we'll check 0 plus and limit 0 minus, right? So let us check first the right limit. So 0 plus, 0 plus means we will consider the floor function, that means floor function of h minus 0 by h. So okay, so we're tending to 0, we're tending to 0, h tending to 0 from the positive side. So then what will be the floor function of h? It will be 0, right? So we will get 0 by h, which is equals to 0. And what is the left limit? That means the box function of h, right? Minus 0 by h. So again, if 0 is, h is tending to 0 from the negative side, and here we are taking the box function, that means it will be the value of the value of ceiling function will be 0, right? So again we will get 0 by h, which is 0. So we can check that both left and right limit exist and they are equal and equals to 0. Okay, hence f is differentiable at x equals to 0. Okay. Okay, let's move to the next question. This is the fifth question. So we can check, we can directly after seeing the graph, we can see that we can draw the graph with a single drag, right? So the graph is clearly continuous. And what about the differentiability? So what is f dash x? We have fx equals to x power 1/3, right? So fx will be, f dash x will be 1/3 into x power minus 2/3, right? So this function is clearly defined at every point except x equals to 0, right? So the domain is just x not equals to 0. Hence we can imply that f is differentiable on r except at 0. Okay, that means f is not differentiable at 0. So this option is also correct. Okay. Okay, this is a sixth question. We have the function fx equals to x Okay, so we know that f1 of x equals to x and f2 of x equals to mod x. So both the functions are continuous, right? f1 and f2 both are continuous. And if f1 and f2 are continuous, then multiplicative function of f1 and f2 is again continuous, right? So this function is continuous. Okay, that means f1, f2 are continuous. It will imply f equals to f1 f2 is also continuous. Okay, so this is continuous on R. Sorry. Okay, now we can break the function. This will be minus x square when x less than 0 and x square when x greater equals to 0. Okay, we will check the differentiability now. So limit h tends to 0. At 0 we will check the differentiability. Okay, so 0 minus, then it will be minus h square minus 0 by h, which is minus limit h tends to 0 h, which is equals to 0, right? Similarly, h tends to 0 plus h squared by h will be equals to 0. Hence both the left and right derivative exist and they are equal and equals to 0. Okay, so the function is both continuous and differentiable. Okay, let's look at the eighth question. So we have the sine function, mod of sine x. So we know that the graph of sine x is like that, right? Right, so when we take a mod over any graph, we just flip the graph with respect to the x-axis, the negative portion of the graph. Okay, that only the negative portion of the graph with respect to the x-axis. So if we take mod of sine x, so the graph will be then become this type of thing. Okay, so you can observe here, we have just flipped this portion of the graph here, this portion of the graph here, and so on. Okay, then we will find this type of thing. Okay, so 0, pi, 2 pi, minus pi, and so on. Okay, so you can clearly see that it is basically repeating after pi, right? So after pi, it's the same thing going on. Okay, so this is basically a periodic function of period pi. Okay, okay, it is everywhere continuous and differentiable. Okay, so if we check at the pi, I mean 0, pi, any n pi, for any n belongs to integer, so we will get a sharp corner like that, right? And we know that if there is a sharp corner at some point, then at that point unique tangent is not defined. That means at that point the function will not be differentiable, right? So at any n pi, for any n belongs to integer, the function will not be differentiable. Okay, but the function is continuous everywhere. So we can directly see the graph. We can draw the graph with a single drag of the pencil. So it is not everywhere continuous and differentiable, but it is everywhere continuous but not differentiable at n pi. So this option is correct and this is incorrect. Okay. Let's move to the next question. So there is a graph given. Now we have to check the options. So there are some points in the interval minus 5, 5 at which the derivative of f is 0. So clearly we can check this is the point between the interval minus 5, 5, right? And the derivative at the point is basically 0. Similarly, at this point, the derivative is also 0. So there are some points at which the derivative is 0. Okay. Okay, so there are points in the interval this at which f is not differentiable. So f is basically like that in the interval. Okay, so clearly there is no sharp corner, right? At a brief point of the graph in the portion, we can draw a unique tangent. So at every point, the graph is differentiable. As this option is incorrect. Okay, this is also Incorrect. There are 2 points where the derivative of f are non-zero. You can clearly observe that the graph is basically repeating, right? If this is a graph, right? So this is the graph of a sin x. You can clearly get it, right? So what is the derivative of sin x? The derivative of sin x is cos x, right? So we have cos x, and we have minus 5 to 5. This is our minus pi, and this is our pi. Sorry, this is 0, this is pi, and this is minus pi, right? And the interval is, that means minus pi to pi. This interval is basically a sub interval of, that means a subset of 5 by 5, right? You can see this is the interval minus pi to pi, and this is the interval 5 comma. So this is clearly a sub interval of minus 5 5, right? And we know that cos function is a 2 pi periodic function, so it will again repeat after 2 pi cycle, right? So after this, when it will cross the boundary minus pi to pi, it will start repeating the values. Okay, so we will definitely get at least 2 points where the derivative will be same. Okay. Okay, this is the last question. So we have a function. Given that this function is continuous and differentiable at x equals to 1, so we have to calculate the value. Okay, if the function is continuous, then we know x tending to 1 minus fx equals to f of 1 equals to limit x tending to 1 plus fx, right? So let us just put the values. 1 minus, because we are taking 1 minus, we will take this function, which is kx square plus l equals to f of 1. So this is equal here, so we will just put 1. So we will get k plus l equals limit extending to 1 plus lx square plus kx plus m. Okay, so from here we will get k plus l equals to l plus k plus m, right? So from here we will get basically m equals to 0, because k plus k can be cancelled out from both the side. So now we have the value of m. Okay, so we have m equals to 0. Now we also have that f is differentiable at x equals to 1, right? So we will apply the definition. So limit s tends to 0 plus f of, if it is differentiable, then 0 plus f of 1 minus h minus f of 1 by h. This will be equals to limit h tends to 0 minus f of 1 minus h minus f of 1 by h, right? So when h tending to 0 plus, minus h will be tending to 0 minus, right? So 1 minus h will be tending to 1 minus. Similarly, when h tending to 0 minus, then 1 minus h will be tending to 1 plus. Okay, so we will apply the definition accordingly. So we will then get limit is to 0 plus, because this is tending to 1 minus, so we will take this definition. So this will be k into 1 minus h square plus l minus k minus l by h, and here we will take this definition, h tending to 0 minus l into 1 minus h square plus k into 1 minus h, and we will not take m, because we know m is equals to 0. Okay, minus k minus l by h. Okay, so we know that we can observe that both the limited in 0 by 0 form. Okay, so we will apply L'Hospital rule here. So then we will get 2k 1 minus h minus by 1. Okay, and it is equals to hence tends to 0 minus, if we do the derivative here, so similarly 2l minus 1 minus h minus k by 1. Okay, now we can put 0 instead of h, so we will get minus 2k equals minus 2l minus k. Okay, so we can take all the terms in one side of the equation, then we will get minus k plus 2l equals to 0. Okay, that means k minus 2l equals to 0. Okay, so we have to calculate the value of k minus 2l plus m, which is 0 plus 0, which is equals to 0. Okay, so 0 is the answer. Okay, so that is how we can calculate this type of problem. Okay, thank you.